be discussing some SSD architecture challenges with framing this from a DRAM perspective, but it's not going to end up being just DRAM. I'll go through what is an indirection unit, why do we have them, and solving the IU capacity limits, and then the customer ecosystem for these large indirection units. With the history of indirection units, we actually have to go back to HDDs. In the beginning of time, we had cylinder head sectors. I kind of equate this as kind of an open channel of HDD. And it eventually happened that 512 bytes was kind of dominant in the marketplace. And that moved over into SASE and ATA. And there were established 512 byte sector sizes then. And so from HDDs, we started with this 512 byte sectors. But they noticed in HDDs that there was an inefficiency in the ECC, and it was kind of, as a percentage, is kind of growing to be too dominant. And they, as an HDD format, storage format, they moved over to, they had the advanced format technology group, eventually making a decision and agreeing on a 4 kilobyte sector size here. And it was a big effort. Customers, vendors all agreed upon it. And it showed some good ECC gains. And they partly picked this to align with some of the memory page size allocations that were happening at the time in the memory management. So storage and memory management alignment were a benefit. While HDDs agreed on this format, it ended up that SSD, enterprise SSDs really started shipping basically 2007, 2008. And so at that point, they kind of knew that while the first HDDs that were shipping with 4 kilobyte native, or I'm using 4 kilobytes, were really shipping in 2010. But even with the first SSDs, they knew that these 4 kilobytes were going to be a dominant place in the ecosystem. So they started from a perspective of they knew that 4 kilobytes was going to be pretty dominant. I get lazy with sector, block, and LBA. As a device side person, I kind of use them interchangeably. I know that sometimes in the host software layers there's differences. Forgive me. I'm not an expert on those. From an SSD perspective, we look at delivering both the 512 bytes and the 4K kind of as the same. So we might lay it out on the disk here. I have some example potential layouts for 512 and 4 kilobytes. And we have a separation with our logical to physical table here diagrammed. I have the physical pointers actually drawn pointers here for illustration purposes, but we can have the first 8 512 LBAs, and the first 4K can be tracked together with one physical pointer, so that L2P table for doing the logical to physical translation. And if you were to do a write for a 512 byte sector, we're going to have to do a read, modify, write. We got to read out any of that missing data, modify the segment and data, write it back to the NAND for storage. And additionally, SSDs need to do a garbage collection. So we're going to, of course, need to have that separation so that we can continue to move the data around as we do garbage collection. That logical to physical table will be in place to do that translation always for us. And we're going to end up doing, in the simplest representation of L2P table, as I'm showing here, I just make it an array. I am ignoring namespaces to keep things a little bit simpler. I don't think it's going to be astronomically much of a stretch. It's still representative of what we do in the drive. But having this separation of the logical to physical allows us to have the movement of that data when we do the garbage collection. So we can keep that physical pointer moving whenever we transition the data around. I've already started to break you guys into it. I am using, there's a cross between memory and storage here. So I am using the metric and IEC so I can separate actual gigabytes and gigabytes and I'll be transitioning back and forth because it ends up mattering a few times later on. I don't use the metrics that you'll see over here in this memory column, which is pretty common in the industry, but since I'm going back and forth, I focus on the two columns that provide the clarity there. So I do try and say kibibytes, 4 kibibytes through this presentation for that purpose. From a physical and logical capacity perspective, we all know the basic definition of over-provisioning. Historically, this was used, maybe you could look back and you could say, okay, we're going to have 8 128 gigabit die, and you have 8 of them, so we have 128 gigabytes of physical capacity, and then we can move that over to a 7% over-provisioned drive by saying 128 gigabytes. So 128 gigabytes versus gigabytes, sorry, is where we get this nominal marketing 7% OP. And then we mixed it up even more with an industry, and we added in the fact that our logical capacity is going to degrade by having bad erase blocks showing up on our logical capacity. So we really, as an industry, were really confusing things there. We ended up further shrinking things. So now, today, some nominal capacity is written out. We shrank that 128 gigabytes to 120 gigabytes. And this was not all SSD's faults. It's also bad sectors growing in HDD as well. So both storage mediums kind of shrank that logical interface capacity. But the big thing here is that that 7% OP is really a shorthand. I like to call it a marketing OP just because it's a communication shorthand. It's rarely true value for actual over-provisioning of a drive. We're going to have extra erase blocks for helping yield, and we also have other things like TLC NAND that don't even allow us to be a nice, pretty power of 2 very easily there. So when we look at L2P table and we have a 4 kibibyte LBA size, if we set that up for our indirection unit size, and we have maybe a 960 gigabyte SSD nominal capacity point, when I look back at that last slide and I say, okay, we had all this confusion on the lost capacity, we actually have 960.2 gigabytes. This is a edema capacity point. And just so that I can be held to the highest standards, not that it actually adds to any clarity, I do the math for edema capacity here. And if we were to track this with a 32-bit indirection unit tracked, then we can see that we're going to track it. The DRAM consumed by the L2P table is going to end up being 937.2 megabytes. It's not exactly the 1,000 to 1 that gets often quoted, but it's close enough. It ends up being 1024 to 1. This is the amount of storage tracked for 4096 bytes divided or in ratio to the 32 bits to track it. And this is an important metric I put up here now because ideally we would like to track more storage for less cost of DRAM. So we would prefer to see this ratio increase. That's better cost ratio for our customers. And I'm putting this up a few more times for comparison so that we can circle back to this and get a feeling for how much the cost of the DRAM is increasing within the context of an SSD shipping. When we look at an embedded environment, I have just an example system here today. There are a lot of other variations. We have an embedded core SRAM, and we have our DDR controller that, in this example, is going to put on the ECC inside of our ASIC before it goes as stored in the DRAM. The reality is these are embedded cores, so they're 32-bit SRAM and 32-bit processor. The same can be said for DRAM. A common interaction might be this kind of a model where we have 32 bits of data and we're going to have 8 bits of ECC that are going to be applied over that so that we can have SecDed coverage on our data when it's in DRAM. Yes, I'll note that LPDDR5 is starting to solve this. I didn't need to get into teaching everybody LPDDR5, so we're going with this model. It's relevant enough. The big thing to take away here is that our processors, our SRAM, and our interface to our DRAM are all 32 bits in an embedded SSD controller. That's really where we're focused on. That's the big takeaway that we're looking from this slide here. This is in contrast, of course, to the hosts. Much bigger addressing, processing, and then their memory, of course, is a tremendously better bandwidth into their DRAM. If we were to look at our physical addressing options, how we're going to track where our memory is, then we could go through and do the compact simple math here, right? So if we had 1 bit, we could track 2 locations on where we tracked things. If we had 2 bits, we can locate 4 different positions of where we've stored data and onwards. So we find that we're eventually locating a total maximum of 2 to the 32 locations for how much data can possibly be tracked with 32 bits. And of course, this simple math is a problem because we need to translate it. Where is it actually, right? NAND isn't just drawn like this on these boxes, right? We need to actually do a lookup. What die is it going to be on? What plane is it? Which erase block? And onwards, right? So there's actually a translation that will actually happen within the drive if we use this compact simple math. And that's okay. We can do that. That's something that can be solved. The other option, equally valid. I'm just pointing out that both of these are valid methods and they both end up getting to the same solution. You could assign a physical meaning, right? So I have this pretend little drive over here that only has a total of 12 NAND die. And so when I say 12 NAND die, I'm going to assign 4 different bits to those die. And I end up with something that would, these 32 bits have an assigned meaning, right? But of course, when you see this assigned meaning, you can see that we end up having these gaps and inefficiencies. It's not a huge thing. We have those gaps and inefficiencies when we do the compact simple math as well. But either way, the real takeaway is just to hammer home, yes, we have a way to define this physical pointer, and we still end up being limited to 2 to the 32 is the maximum trackable locations, no matter which way you look at it. Well, okay, so we have maximum trackable SSD capacity. We have 4 kibibytes of stored data tracked, and there are a total of 2 to the 32 locations. So we can ship a max capacity of 16 terabyte drive. All right, we're done. Except that we're still shipping larger drives. So how are we looking at solving these in the ecosystem? And of course, we started out with indirection units being the conversation. So what are some of the solutions here for getting past this indirection unit challenge here? One is that we could increase the bits per L2P entry. We could increase it to 33 bits for a 32 terabyte maximum capacity drive, 34 for each one. We end up having this concern that our DRAM accesses are still optimized for 32-bit. And it's really, again, our processors and SRAMs are also 32-bit as well. We're really focused on a 32-bit world right now. Or the other alternative, instead of bleeding out to 1 bit for each doubling of capacity, is that we have some compaction in order to access these larger 33 bits, right? There's going to end up being a read of the 32, and then the next 32, and so forth. But then, depending on what size your L2P entry is, you can end up having something, as I've drawn here in red, where we're going to end up actually sometimes having to do 3 reads, depending on the L2P entry size. But the other problem with this, and this is where I've circled back to that ratio, is that if we've gone to a 33-bit L2P entry size, then we have 31 bits of unused space if we were to not compact it, right? So there is a way to save all this reading and back and forth, but it ends up being a big cost on our DRAM. So we we know our customers don't want to see that doubling of their DRAM cost and size there. We could do trade-offs and we could focus in on, say, 40-bit entries. This enables something up to 4 petabytes as max physical SSD capacity. And then we just focus in on one offset and compaction, right? So it's an 8-bit shifting rather than something that's dynamic with every size. These are the kind of trade-offs that we would be able to look at and examine. Which ones do we prefer? But this 40 bits still has a max capacity of 4 petabytes, so it's going to have an end of life as well. It ends up being that this increased bits per L2P entry is going to hit us on cost and performance. There's going to be a cost of the DRAM size increasing. And of course, there's going to be latency increases with each DRAM read back and forth for each of the pointers. And that is, of course, is increasing the DRAM traffic. So there will be more congestion in through that small wired interface, right? So I actually drew that DRAM interface in part to hammer home the fact that in order to get the data, we're chugging out through the same thing. We don't have that parallel access, right? It's 5 different transmissions out to the DRAM, whether it's a read or a write, either way. Another option, instead of increasing our L2P table entry size, is that we would look at some wear leveling subdrives or some domains that we look inside of. So this is another solution that we can evaluate. So we would stripe or hash the data into these drives based on their LBA. And there's a lot of schemes that can exist. Within those subdrives, once we're there within the subdrives, of course, we can implement a miniature L2P table within each subdrive. We then have problems that there's a goal of, we have all of this NAND available. Ideally, we would love to be able to wear level and balance between this, right? We have all this extra capacity. Let's use the extra physical capacity to extend and provide the best endurance for the drive. This is more challenging and requires some invention. But even if without that invention, it may not even be acceptable to some customers. But generally, this is within each subdrive, you have a maximum physical capacity of 16 TB, and that's a pretty good amount. So when you do wear leveling within 16 TB, it doesn't seem that bad that the wear leveling shouldn't be hindered amongst that much storage space. We do have L2P entry size savings. So depending on how many subdrives you have, you can shave off that many bits, and so you're able to keep the subdrive count increasing as you need to increase that size of the shipping drive. So just summarizing this option, we get to some endurance concerns on the global wear leveling. There is a performance question mark. Without some careful design, there can be a risk to loss of parallelism. And there can be extensibility risks or questions on how do you make those global NAND decisions. That's going to be something that you need to solve carefully. Increasing the IU size is generally an industry standard. It's showing up pretty common in the industry. And it's a similar solution as emulating the 512 bytes LBAs that we saw from HDD and those early SSDs, right? So there's this advantage that we've seen this in the host before. We're aware of it, and so extending that and using that legacy knowledge is helpful. Of course, all of us have seen in the 512 byte interactions, misaligned or smaller interactions are going to cause a read, modify, write for those indirection units. And with indirection units continuing to increase and then the host stack not changing, the interaction size is actually going to more and more see those read, modify, write performance penalties on their writes. So I have this diagrammed here, just moving to an 8K indirection unit. And the nice part that you can see here is that we move our amount of stored data to the cost of the DRAM is moving in the correct direction. This helps our cost on our DRAM drop off. So that's appreciated. And just summarizing this option again, I kind of spoke through these. The performance and endurance questions on read, modify, write interactions. And there are good improvements on the cost and the legacy compliance intuition. And of course, you can mix all of these solutions. It's possible to mix them all. For example, there's a possibility of having some wear leveling subdrives and have them as large as possible. And then once you have them as large as possible, then you can increase your indirection unit to minimize the read, modify, write performance impacts. From an IU size in SSD's perspective, could we solve this from similar to what HDD? Can we learn from them? Can we as an industry look at this and say, let's pick an IU size and stay there? And generally, I went through this in great detail in part to make sure that it's clearly described on why we're seeing these limits, right? So we can't, whereas HDD, we were seeing a loss of efficiency, a loss of storage efficiency as we were having too much ECC as a percent to data stored. But we're not really looking at doing it for those reasons in an SSD. It's more for the cost of the memory, the size of those interactions. And so it's different reasons that we've arrived at this limitation here. And so with an enterprise customer base still focused on low cost, optimized endurance, high performance, and I also emphasize tight latencies. Tight latencies is here because in client SSDs already, they have a possibility of paging in and out an L2P table so that they can maintain an IU size. If you're paging in and out a table, then your tight latencies are in violation. So until we get to an ecosystem where our latencies are allowed to vary more in an enterprise environment, we're still going to be focused on those tight latencies through our entire capacity of access. So at this point, without that solution, we're really kind of ruling out that advanced format type of effort that HDD saw. And for now, IUs are going to continue to increase. So now what do we do from that perspective of a customer ecosystem for these large IUs? Since they're already bigger and they're going to get bigger still in the future, one possible solution is similar to the legacy, right? We had the LBA sector format for the indirection unit, and we could grow that. So there is precedent. The 4K IUs match their sector size. And the system overhead reductions are possible, right? You could have longer PCIe TLPs. You could have other transfer efficiencies as you transfer these larger sectors through the system. There are potential advantages in the ECC efficiencies, but the reality is if we're going to be storing data at an IU size, independent of whatever the sector size on the interface is, we can always go and make those ECC advantages true at any point because we're going to read, modify, and write the whole unit. At that point, we don't care what the interface is anymore. So we don't need the sector size format to change on an SSD in order to get those same advantages. From a perspective of why we should not change the sector format size, there's still a significant 512 byte usage after years, right? So the advanced format group was recommending 4 kibibytes in 1998, and then native drives were shipping in 2010, and I don't see any end of the 512 bytes in our future. I think it's going to continue, that we need that access size for the drives. So I think that we're going to have to support various LBA sizes no matter what, and we're going to need to support those various LBA sizes from the perspective of every single time we ship an IU size. Do you want the sector format size to change? That's going to really blow up the ecosystem of what are all of the sector sizes that need to be, the host ecosystem need to be ready for. I don't think that a host wants to see or be prepared for 8 kilobytes, 16 kilobytes, et cetera, in all of their formatting. When you get to extremely large IU sizes, especially when you get out to 4 petabyte drives and those large drives, then you're going to probably need to come back and readdress the protection information standards for the larger sector sizes. The other thing that we found from, not myself, but those that contribute and look in the open ecosystem software storage area, they said that the memory pages are tied to sector formats. There's a lot of assumptions hidden between the memory paging and the storage block size. And so we don't want to be ready for all of those sector changes and all of the knots that will be discovered there. And then the reality is we have a lot of software today that's focused on 512 bytes or 4 kilobyte interactions, and so they have a risk of performance degradations depending on how you set up your ECC and things like that. It would be a potential risk. So let's look other places. Within NVMe, we already have the parameter from the optimal performance parameters that were standardized there. There is an NPWG parameter that specifications have a challenge. You don't want to speak about the physical things because what happens if it's an HDD shipping with this parameter versus an SSD shipping with this parameter? So in standards, you can't quite say, make this your IU size, right? That's not quite acceptable in a standards document. But as much as possible, it was highlighted that make NPWG equal to 4K or your indirection unit size there. I think OCP really helpfully came along and just said, do it. They took and closed that gap that NVMe couldn't quite do, right? So they said, set this equal to your indirection unit. So I like that, and I think it should be propagated. Add in that NVMe has atomics parameters. Here I'm highlighting the atomic write unit normal and the namespace atomic write unit normal. They're, for the purposes of this discussion, they're the same. And basically, they force an ordering of if you had a read in flight in the system and a write, or multiple reads in this example in the upper right, and you have a write in the system, it's going to make sure that you either get all old data or all new data. So it forces that ordering when you have an overlapping LBA reading. The power fail adds on to that it'll be, when there's a question of when power fail happens and you had a write in flight when the power fail happens, it'll add in what happens and define that. So the power fail exception basically says that we have smaller boundaries, and within those boundaries, we will have the atomic consistency. I think another thing that relates to this really well, I would be remiss if I didn't mention a little bit, is multiple atomicity mode. When we have a write that's very large, shown here in orange, you have those AWUPF boundaries that are quite small fitting within. The multiple atomicity mode says within section 1, 2, and 3, individually, they will either complete atomically or not complete atomically. So if this write was in flight and a power fail happens, a host could come in, do a check on each of these 3 areas. Perhaps if there's a timestamp, they can do a check and see which one is old and which one is new, and this may, in the host, be reducing how much needs to be rebuilt afterwards, right? That's a possibility. But focusing in mostly, I think AWUPF is a very helpful parameter. Within the host, you can look at these atomics, and basically, while they're well defined as to how they'll behave, the ability of the host is to build those up into a coherence and consistency model across the multiple host compute resources. From a coherence perspective, the requirements are that the writes propagate to each of the processors at a similar time, and there's a transaction serialization, right? So within the context of when a command completes, there are question marks, right? I have that shown in orange. So whether a command is before or after the command is clearly going to be the old data versus the new data. There are questions while the commands are in flight. The same questions end up happening with consistency, but with consistency, there's a requirement for all processors to be consistent in the order that they see the data. And so the big takeaway is that with the NVMe atomics rules, you can build up your preferred coherence or consistency requirements based on what model you want, right? There's too many flavors of coherence and consistency, and a drive is able to be a component if a host sets up their expectations based on the right submission and the right completions and their synchronizations. And I should have popped up my conclusions there. But AWPF allows that assumption of the size of the write for that consistency and coherence, and across power fail is one of the important things. So some coworkers at Samsung, our open ecosystem team, has been leading a large block size effort in Linux, and they've evaluated the OS changes, and they've been doing this to facilitate these QLC drives, and actually all large capacity drives. A TLC drive is also able to have a large indirection unit and quantify the software impacts. And they've been propagating those through all layers. They've found that LBA size, they don't want to change that. It's too difficult. So their focus was to propagate the AWPF and recommending that we want to have an indirection unit set equal to NPWG as recommended by OCP. And of course, there are customers out there that don't follow OCP boundaries, right? This is a recommendation that we begin aligning the ecosystem around this. And then we want AWPF, the power fail, to be greater than or equal to the NPWG, which is going to be equal to your IU size. This ends up having minimal ecosystem impacts. There's no backward compatibility concerns because any changes that they are dependent upon for the atomic power fail are going to only move with the drive moving that up. So a drive today that might not follow this, this recommendation might have a very small AWPF and a large IU size. This LBS work will still focus in and only assume atomic interactions at the size that's promised by the drive, right? So there's not going to be any loss of data, any problems there. Multiple atomicity mode is kind of like keep that card in your back pocket. So far, the LBS work has not found advantages for using this, but it is something that I think should be still in the conversation. Their changes are shown here in black. They've encapsulated all their changes, right? So it's one of those things where you don't necessarily need to do the work to get the advantages of this. And the one thing that you might do is the IO alignment determinism is an option in order to help the host IOs further align with the atomics. But they've propagated these changes, and they have them expected in the next version of Linux. They've provided this work where they have modeled the performance improvements. Let me see how I'm doing on time. Yeah, so we can go through this a little bit. Let me bring over. So on the top row here, we start out with an indirection unit of 16 kilobytes or 64 kilobytes. And we have a file system block size, which is the interactions that the host has with the drive, right? So the drive is 16 or 64K IUs, and the file system continues to interact at 4K. And with buffering, they still see enormous write amplification on the drive highlighted in red there, right? So at 64K, those are larger IUs. We, of course, expect those read modify writes to happen more frequently. So that's our baseline, is the top two rows. When you continue on and you look at the changes that LBS has integrated, they were able to have write amplifications due to the read modify writes, which is what they're focused on, driven nearly to zero. You can see that it's, what is that, 6 decimal places on this third line here for the 64K interactions. And they continue to move on, whether that's buffered or direct I/O, they show these same advantages. You can see the fact that it's 6 digits of accuracy and not all the way out to 1.0 infinite is that there is some final work that they're going to be continuing on. And they've propagated this again into some example workloads here with MySQL and interacting with a 16K indirection drive or a 64 kilobyte indirection drive. And similarly, they see the same advantages and results. So they've propagated those changes and not had to touch those upper layers. And then also, just for further understanding, this particular one that I've highlighted right there, we move on, and if we were to look at that data trace, how many interactions are at the 64 kilobyte interaction size or larger, right? 64K or a multiple thereof are all acceptable for minimizing the read modify writes of the drive. You can't even see there's 3 4K interactions. There are 3 8K interactions. And then if you were to look at the offset of their, the LBA that they were offset, there's again a count of 3 and 3. And so those are the final couple that they're going to track down and close off as well. But overall, they generally have aligned their interactions pretty well with the IU size based on the parameter AWUPF being greater than or equal to NPWG. So why am I continuing to bring up AWUPF greater than or equal to NPWG? I focus on that because it just ends up giving the vendors some more design freedom, right? Because often, as a drive vendor, we will design the AWUPF within the SSD controller, but the IU size can vary with every capacity. And so we might have one drive that we've generated with several capacity points. That AWUPF might be constant for the entire capacity range, but the IU size might possibly be changing. So it gives that freedom to continue to disconnect those two developments. And I think that it is nice to also describe what is going on here, because it's possible that if we had an AWUPF equal to an extremely large value, one megabyte, then perhaps that's really hard to aggregate up that much data interactions there. And so from that perspective, there's an option where maybe when we get to that extreme AWUPF size, then maybe you just want to go up to NPWG, which is the IU size, right? That's an option for the future. I don't think that it's a problem for today, since we haven't grown to those enormous AWUPFs yet. But overall, I hopefully have explained why IU sizes are going to continue to increase. They're definitely going to continue to get larger for the immediate future. Recommending that we begin to have new customer requirements being aligned on AWUPF greater than or equal to NPWG, and reporting IU size in NPWG. And I think that it's really nice that all of these are backwards compatible, and that LBS is already part of Linux Next. We expect it to be part of the next kernel release. I think you can also learn more with Hyung-Suk Kim's presentation on Wednesday. So welcome any questions at this point. That's my presentation. Thank you. Thanks.
So when the IU is large, and if IU, for example, 16K, if the host send 4K times to fill up the IU in 4 small writes, but that generates read modify, right?
The question is, if we have a large indirection unit and a host is well behaved in that it's going to send a 4K followed by the next 3 4Ks. So the example is a 16K indirection unit, and we sequentially write the first 4K, the next, and the next, and the next. So eventually all 4, the whole 16K is provided and written by the host, and then that will be gathered and flushed to the drive, and it removes the read, modify, write. I've focused and tried to say from an industry perspective what can be expected from every drive, right? Because I'm advocating for an industry perspective. And so from an industry perspective, you cannot depend on that erasing all read, modify, writes. There is a possibility that every 4 kilobyte write would cause a read, modify, write in the drive. Having experienced several different architectures in my own career, I think that it is very common for that to get buffered and captured. There is a little bit of a question mark on how quickly you do the writes, right? There's a time process where we, as a drive, have a set amount of data that's in flight. So there's not an infinity promise, right? So if you do one write and then 2 years later you do the next 4K write, it probably got flushed. But I think that very commonly in the industry, you will be mitigating and not really seeing, you'll be buffering there, but no, it's not 100% promised.
So if this write pattern is interleaved with other IU aligned writes, do I still get almost no read modify, right?
Yes, so this is a better question. So take that same example and now interleave other traffic and have other writes going on. So one particular thread might be behaving nicely, eventually writing all 4 contiguous sectors. And that is a huge, especially in a conventional SSD, that would be your biggest window of no, it's going to end up getting flushed by the time, if a drive doesn't have any knowledge or context, it doesn't know to keep that data, right? So it's going to want to efficiently use that write buffer, not depend and assume on what is coming in the future. So it's going to assume that it cannot assume the next data is coming and it needs to flush. It'll do the best greedy usage of its write buffer is the normal expectations of behavior. And actually, knowing our prior conversations, I'll also continue. I was careful to say that's a conventional drive. I know your follow-up question is, what if it's a FTP drive and you have identifications for this stream of data going to this RUH versus another? I think it'll end up being a vendor-specific answer, but similar to my first answer on conventional drives where an industry norm is to buffer, and as long as it's coming in sequentially and in relevant time, probably it's a good, reasonable belief that they will be successful in identifying those. But I don't think you can always depend on that. Yeah.
So let's follow up on that. So when you mount a file system, either XD4 or XFS, whatever, I see that they normally look up at the optimal IU size in order to do the stripes, right? In order to align that, so when you do buffer IO, you have that alignment. And I've seen a lot of drives not following up that, and your optimal IO size, IO size actually, is much larger than the IU core. I've seen now in Gen 5 drives where the MPWG is populated, even though the drive is a 4K aligned drive, and that causes the file system when you mount is there any standards on how to populate an optimal I/O size that comes from the RAID idea? When you have the RAID, that's where you have that optimal size.
Yeah, let me try and summarize. You had a good depth of question, so trying to summarize. So one is the NPWG is one parameter, and NOWS is a nominal optimal write size, and it's much bigger. Thank you. So the first question is, what's going on there? The short answer is that, so NPWG is really focused on the IU interactions, but NOWS is really focused on good striping within the drive, and so you'll get interactions of, is this drive choosing to stripe data across one NAND die for full word line programming, or maybe it's striping across many die for many parallel word lines. So generally, the answer of why NOWS is much larger is because you want to take full programming parallelism capabilities of the drive. So it's a performance, NOWS is a throughput performance parallelism and buffer sizing parameter. So it's set by, NAND parallelism buffering. NPWG is set on avoiding the read, modify, write penalty. And so out of the two, NPWG being set equal to IU size is a lot more follow that direction. NOWS is more aspirational, and it's acceptable if you don't hit NOWS, right? The idea is that it'll help you if you do. So that was one question. The next question you had was that right now in industry, we don't have a lot of uniformity of having NPWG always set to IU size. And that is true. And that's partly why I'm publicizing, hey, let's start getting some uniformity. So I'm hopeful that customers start adding some of that. In OCP, it's, to the best of my knowledge, it's the most companies coming together on these type of customer requirements. But certainly, there are other companies that don't align to those OCP requirements. And I'm encouraging them, even if they remain otherwise, start aligning your NPWG requirements over. You are correct. I've actually seen some customers will tell us as the drive to set NPWG to other values. I don't really know their reasoning. Maybe you're right. Maybe your guess on it being equal to a RAID parameter on their side, I don't know. But right now, NPWG doesn't always equal IU size. Good news is AWPF is the parameter of consistency and coherence, and that's the critical parameter, right? When we increased AWPF to that larger size, that allows the file system database metadata to move up to the AWPF size. Until AWPF is big enough, the metadata has to stay within the AWPF parameters. So metadata for those file systems database was always going to be a blocker until we we grow the AWPF. So to me, the critical metadata for those file systems and databases is the key enablement there. Actually, let me get somebody else's questions. And yeah.
So staring at your table of data in 26, is there any reason to do a 16K IU when 64K IU looks almost identical?
AWPF parameter might, for each drive or vendor or generation, you want to go up to your AWPF, right? So if you only have AWPF up to 16K, then you can't go to 64 on consistency. That being said, for example, the lazy database updates and things like that, where it's not your file system metadata, yeah, go crazy. The bigger the data command, I'd always ask for bigger commands. That's lovely. Give me more data anytime you can. Higher queue depths too. But yeah, I think you want to go up to maximize that AWPF. The one secondary, less important answer for why you would not go all the way up to a 64K is if you're focused on file system metadata, it's like, I don't know the sizing, but you're tracking, it's metadata, so it's 64 bytes tracking, 1 megabyte of data, so you only need 64 bytes. And so from a host file system perspective, you buffer all of those things up to AWPF, but you don't want to buffer up to enormous because you're still doing, at the host side, you're doing those 8-byte or 64-byte interactions. So it's I think, a balance, and it's more like give the host the ability to make these decisions.
So what happens if 5 vendors have 5 different IU sizes in the same generation? Will the host be able to deal with it?
Yeah. Set your AWPF. So the question was, if 5 vendors in one generation SSD all have different IU sizes, and I'll even make it worse than the initial question, every vendor has a different IU size for different capacities, which is possible. Yeah, are you okay? Yes is the answer. Query your drive's AWPF, and query your NPWG, and you want to move up to the minimum of those 2 values, right? Which is what the LBS is doing. Yeah, so I think that it is. So I ran out of time. I'm available for questions, and I'll be around the rest of the 3 days here. Thank you.